Welcome friends, Igor is here, and in this video we will discover a new vector space structure. Its vectors are linear transformations. In this lesson we will learn how to add, scalar multiply, and compose linear transformations, prove that these operations result in new linear transformations, and we will observe that the set of all possible linear transformations between two fixed vector spaces themselves become a vector space. Let's get started. If we have two linear transformations from a vector space U to a vector space V, then we can add them up, and the definition is the usual definition of the addition of functions. Notice that the plus sign on the right-hand side of this equation is the operation of addition of vectors in the vector space V. Let's prove that when you add two linear transformations, the new function is again a linear transformation. We will do this by checking the two properties of linear transformations. First, we compute the value of this new function t plus x on the vector x plus y. We use the definition of the function t plus s, and then we use the assumptions that t and s are both linear transformations. Then we use the commutative property of vector addition. Then we use the commutative property of vector addition in the vector space V, and we notice that this expression is the value of the function t plus s on the vector x plus the value of the function t plus s on the vector y. And this computation shows that the function t plus s respects vector addition. Now let's check scalar multiplication. First, we use the definition of the function t plus s. Then we use the assumption that t and s are linear transformations. And then we use properties of vector operations in the vector space V. What we have in parentheses is the value of the function t plus s on the vector x. And this computation shows that the function t plus s respects scalar multiplication. Therefore, the function t plus s is indeed a linear transformation. Here is an example to illustrate this construction. We have two linear transformations, t and s, from C2 to C3. Let's compute the new linear transformation, t plus s. The value of this linear transformation on any input is the value of t on this input plus the value of s on this input, and the plus sign here means the addition of vectors in the codomain C3. We know what each linear transformation does to an input, and all that remains to do is to compute the result of this operation in the codomain C3. Next, let's define how to scalar multiply linear transformations. The scalar multiple of a linear transformation t by scalar alpha is a function which is defined as follows. The value of this function on any input from the domain is the value of the original linear transformation t scaled by the scalar alpha in the codomain vector space V. Let's prove that a scalar multiple of a linear transformation is again a linear transformation. Similar idea to the proof of the previous theorem. I will simply check the two defining properties of linear transformations. First, let's compute the value of alpha t on the vector x plus y. This is the scalar multiple of the value of t by the scalar alpha. But t is a linear transformation. And then we use the properties of vector operations in the vector space V. It now remains to recognize these as values of alpha t on x and y respectively. This computation verifies that the function alpha t respects vector addition. Next, let's look at scalar multiplication. Let's compute the value of alpha t on a scalar multiple of a vector x by an arbitrary scalar beta. First, we use the definition of the scalar multiplication of the linear transformation, and then, because t is a linear transformation, we can pull beta in front of the function. Next, we use the associative property for scalar multiplication in the vector space V. Multiplication of scalars is commutative. And let's use the associative property for scalar multiplication one more time, but now in opposite direction. The term in parentheses is the value of the function alpha t at the vector x. But this computation shows that the function alpha t respects scalar multiplication, because we were able to take the scalar beta from inside the function and move it in front of the function. We have verified the two properties of linear transformation, therefore alpha t is indeed a linear transformation. Here is an example of this construction. Let's start with the linear transformation t from C4 to C3. Then let's scale this linear transformation by 2. To do this, we simply scale the values of the linear transformation by this scalar 2. This operation is performed in the codomain C3. But if you think carefully about what we have just done, you will realize the following. We have defined two operations on the set of all possible linear transformations from a vector space U to a vector space V. We learned how to add two linear transformations. The result of this operation is again a linear transformation from U to V. And we learned how to take scalar multiples of linear transformations. The result of this operation is again a linear transformation from U to V. In fact, with respect to these two operations, the set of linear transformations is itself a vector space. This is just mind-boggling. Let's also observe that linear transformations are, on the one hand, simply functions, and we can compose functions. So we define the composition of linear transformations as the usual composition of functions. And as you would probably expect by now, if you compose two linear transformations, the resulting function is still a linear transformation. Let's prove it by checking the two properties of linear transformations. First, we compute the value of the composition at the vector x plus y. We use the definition of the composition of linear transformations. Then we recall that T is a linear transformation, and then we also recall that S is a linear transformation. Now, just recognize these values as values of the composition of S and T on x and y. Similarly, for scalar multiplication, first we use the definition of the composition, then we recall that T is a linear transformation, and then we recall that S is a linear transformation. S of T of x is the same as S composed with T applied to x, and this shows that the composition preserves scalar multiplication. These two computations verify that composition of linear transformations results in a linear transformation. Here is an example of this construction. We have a linear transformation T from C2 to C4 and a linear transformation S from C4 to C3. The codomain of T is the same as the domain of S, and therefore we can compose these two linear transformations. Let's compute this composition. First, we apply T to the input, which is a vector in C2. Then we take the output of T, which is a vector of size 4, and use it as an input of the linear transformation S. We know what S does to each input. We have a formula for S, and all that remains is to simplify the expression. And you see from this computation that indeed S composed with T is a linear transformation. Notice that the composition goes from C2 to C3. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss injective linear transformations. I will see you later.